Swayam Prabha. Digital India. Educated India.
Welcome friends to this fourth lecture of week 5, and in this week we are talking about ion exchange process. In the last lecture we have talked about the percent based saturation, and in this fourth lecture we will be talking about what is the formula of calculating percent based saturation, and we will also solve different numerical problems related to cation exchange capacity. Now, you know what is percent based saturation, we have discussed in our last class. The percent based saturation is basically the percentage of CEC which is occupied by basic cations like calcium, magnesium, sodium and potassium, and they do not consider the acidic cations like H plus and Al3 plus, and because aluminum is very toxic in the acidic condition for the plant, and also with the increase in soil acidity, the aluminum concentration or aluminum toxicity increases in the soil. Now, we have also discussed what are the reasons of high soil fertility in a soil with high percent based saturation. There are three reasons. One is they have little or no acidic cations like Al3 plus, which can show toxicity for the plant growth. Secondly, they have the soils with high percent based saturation also have high pH, therefore they are more buffered against the acidic cations and also different acid forming processes like nitrification, acid rain, etc. And thirdly, they contain greater amounts of essential plant nutrients, which plant nutrient cations like potassium, calcium, magnesium for the use of the plants. Now, let us see how to calculate the percent based saturation. So, the formula of percent based saturation is basically when you have to sum up the concentration of calcium, magnesium, sodium and potassium, and then you have to divide it with the CEC, total cation exchange capacity, multiplied by 100. So, this is basically the percentage of the total cation exchange capacity that is basically occupied by these 4 cations. Now, depending on soil pH, the soil base saturation may be a fraction of CEC or approximately equal to CEC based on different soil pH condition. So, in case of acidic condition, in case of alkaline condition, in case of neutral condition, the percent based saturation varies. So, in general, if the soil is below 7, that is acidic in nature, the base saturation is less than the CEC, obviously, because the CEC will calculate both H plus and Al3 plus also. In the calculation of the total CEC, we incorporate H plus and Al3 plus. So, in the acidic condition which contain high amount of H plus as well as Al3 plus, the percent based saturation will be less than the CEC. Now, at pH 7 or higher, soil, clay minerals and organic matter surfaces are occupied by basic cations, because the alkaline condition, the CEC will be more dominated by the basic cations, and thus base saturation is equal to the cation exchange capacity. Obviously, in this picture you can see in the acidic condition the exchange complex is occupied by Al3 as well as H plus ion, and for calculating the CEC we calculate not only the Al3 plus and H plus, not only this calcium, magnesium, potassium, sodium, which is present in very minute amount in this high acidic condition. So, obviously, the percent based saturation will be very low in this condition. As the pH increases from 3.5 to 5.3, you can see that the exchange complex is now comparatively more dominated by these positive cations, and also however, there is still presence of these Al3 plus acidic cations. So, as the pH further increases, you can see all the exchange complex are occupied by these positive basic cations, and as a result of that, the CEC, the percent base saturation is almost equal to the cationation capacity in the alkaline condition. Now, obviously, this picture is also self-explanatory. So, in the x axis we are plotting percent base saturation, in the y axis this is soil pH. Obviously, as the percent base saturation increases, soil pH will also increase, and it is quite evident because percent base saturation means when the exchange complex is saturated by more and more basic cations. When it is occupied by more and more basic cations, obviously the soil pH will also increase. So, this is the practical implication of percent base saturation. Percent base saturation is an indicator of soil fertility. Remember, it is basically a fraction of the CEC which is counting for the calcium, magnesium, sodium and potassium, and it does not include the aluminum and H plus ions, which are also parts of CEC calculation. Okay. So, now effect of colloid types, let us see what are the effects of different colloid types in the catenation capacity. Now, differences exist in the tenacity with which the several types of colloids hold specific cations, obviously. Now, at a given percentage of base saturation, smectite which have a high charge density per unit of colloid surface hold calcium much more strongly than does kaolinite. It is quite evident because of high amount of isomorphous substitution. The negative charge developed in the smectite is quite higher than that of kaolinite, and as a result the charge density is also higher in case of smectite. So, due to the higher charge density, they can attract this calcium cation more strongly than does kaolinite, because they have limited amount of catenation capacity. So, calcium percent will have to be increased up to a certain percent to satisfy the need of plants in case of smectite. Obviously, we have to apply calcium more in case of a soil which is dominated by smectite, but because smectite has more attracting power for the calcium than that of other soil. Now, kaolinite can supply calcium at a relatively lower percent base saturation. So, obviously, the calcium can be available to the plant with relatively easier way in case of kaolinite than that of smectite. Now, the need to add limestone to the two soil will be somewhat different, partly because of this factor. Obviously, in case of when we add limestone, we add basically limestone to reclaim the soil acidity. So, in case of smectite soil, it will we need to apply more lime than that of kaolinite, because in case of smectite the attraction for the calcium ion is more than that of kaolinite. So, another important point is this graph. Yeah, this graph you can see in the x axis we are plotting the soil pH, the y axis we are basically plotting the effective catenation capacity for different types of clay minerals as well as organic matter. So, you can see here it is showing the kaolinite, this graph is for kaolinite, this graph is for humus, and this is for smectite type of clay. Now, in case of smectite, the catenation capacity is almost constant up to pH 5.5 to 6, because the negative charge which is responsible for catenation capacity in case of smectite type of clay mineral is basically generated from the isomorphic substitution, and isomorphic substitution does not depend on soil pH. When the soil is basically having more pH, that means more than 6, then some amount of pH dependent charge generated in the smectite. So, you can see from there a small slight increase in their catenation capacity or effective catenation capacity. However, in case of kaolinite clay and humus, which is an organic colloid, all their effective catenation capacity is almost dependent on the soil pH. So, that is why you can see it is highly variable. In case of organic colloid, obviously as the pH increases, there is high increase in effective catenation capacity, because the functional groups, aromatic functional groups which are present in organic colloid like carboxylic group as well as the phenolic OH groups, they basically dissociates and produce the negative charge, and this negative charge is responsible for attracting more cation. We have discussed this in details during our organic organic colloid discussion. Now, in case of kaolinite, you can see they produce both positive positive charge with the increase of pH, because they are dependent on the pH dependent charge. However, when the pH is negative or when the pH is low, that means soil is acidic, then you can see the effective CEC is somewhat negative. So, basically in this case also they are producing, instead of negative charge, they are producing positive charge. So, thereby decreasing the catenation capacity. So, this graph shows what are the effects of different types of clay minerals as well as the organic colloid, and what is the relationship of effective CEC and soil pH in this for these 3 different fractions. Now, let us see another important thing, that is implications of catenation capacity. Now, if we see the implication of catenation capacity, the higher the catenation capacity, the more clay or organic matter present in the soil. This usually means that high CEC of clay, that soils have a greater water holding capacity than low CEC sandy soils. In other words, again the higher the CEC, the more clay and organic matter, because the CEC basically are in the soil, the CEC is basically contributed by either clay mineral or the organic matter. So, obviously, when a soil having more CEC, it is understood that the soil have more clay as well as organic matter. So, obviously, as a result of that, the water holding capacity will increase as compared to the soil with low CEC or sandy soils. Now, in case of low CEC soils, these low CEC soils are more likely to develop potassium and magnesium and other cations deficiencies. So, the low CEC soils are more likely to develop potassium magnesium deficiencies. We have discussed this while discussing the percent base saturation, while high CEC are less susceptible to leaching losses of these cations, obviously, because high CEC means high catenation capacity, higher affinity. So, low leaching loss of the cations. So, for sandy soil, large one time addition of cations, that is potassium, can lead to large leaching losses, because soil is not able to hold to the excess potassium. So, more frequent addition of smaller amounts are better. Obviously, the soil with low catenation capacity is more susceptible for leaching loss of those cations, because they cannot attract them. But in case of high catenation capacity soil, they can attract them. So, you can apply one time. However, in case of soil with low catenation capacity, frequent addition of smaller amounts of particular cations are particular nutrients are important. So, the lower the CEC, the faster the soil pH will decrease with time. So, sandy soil need to be limed more often than clay soil. So, when the soil is having lower CEC, the faster the soil pH will decrease with time, obviously, because their positive basic cations are less. When the basic cations are very limited, obviously their pH will decrease. So, the sandy soils need to be limed more often than that of clay soils to increase the soil pH. Now, the higher the CEC, the larger the quantity of lime that must be added to increase the soil pH. We have discussed just this, just in the last slide, because in case of smectite, which has more cation exchange capacity, we have to add more lime to increase the CEC. Sandy soils needs less lime than clay soils to increase the pH to desired levels. So, these are some practical implications of cation exchange capacity. Now, let us see some specific CEC numerical problems and how we can solve them. These are very easy, but before solving them we need to review a couple of things. Now, you know that one element of any substance, that is element, either it could be element or molecule or compound, etc., is basically atomic mass of the element or molecules or compound. So, the mass of 1 mole of hydrogen is 1 gram, you know that. The mass of 1 mole of calcium ion is 40 gram, and the mass of 1 mole of nitrate is 62, which we calculated by 62 grams of nitrogen, that is 62 gram of coming from this 14 gram of nitrogen plus 3 oxygen, that is 3 multiplied by 16, that is 48 plus 14. So, 48 plus 14 we are getting 62. So, in many chemical applications, a mole is too big unit to be easily manipulated. So, in those cases we generally use this unit called centimoles, that is a 1/100th of a mole, that is 0.01 moles, or sometimes we use the millimoles also, that is 0.001 moles. So, basic in case of CEC based chemical equations and applications also, that is why we apply centimoles instead of moles. So, the mass of a centimole of hydrogen is 0.01 gram, because we know that 1 mole is 1 gram. So, obviously, the 1 centimole hydrogen will weigh around 0.01 gram, and 1 millimole is 0.001 gram or 1 milligram. So, the moles of charge are same as moles of anything else. Remember, this is a very important point. Moles of charge are the same as moles of anything else. So, 1 mole of charge is the charge, either it is positive or negative, of 1 mole of ion with either positive or negative charge. For example, an ion such as calcium has 2 moles of charge for each mole of calcium atoms. So, it is basically the valency. So, for each mole of calcium atom, it has 2 mole charges, because it has valency of +2. It has 2 positive charges, so 2 fewer electrons than protons. So, similarly, a trivalent atoms such as aluminum has 3 moles of charge per mole of aluminum atoms. Okay. So, this is how we can calculate the mole charge. Now, the most important thumb rule for calculating the cation exchange capacity is 1 mole charge of any ion will always be equivalent to 1 mole charge of any other ion. So, 1 mole charge, for example, 1 mole charge of calcium will be always equal to the 1 mole charge of aluminum. Remember, I am talking about 1 mole charge, not 1 mole. So, 1 mole charge of any ion will always be equivalent to 1 mole charge of any other ion, irrespective of their valency. So, this makes the mole of charge, that is molar charge, a handy unit when discussing the cation exchange capacity in the soil. So, this equivalent baseline, that is mole charge, gives the equivalent baseline for calculating the CEC in the soil with more easier way. So, in soil, a mole of anions or cations is too big number to be easily manipulated. So, the most common unit when CEC of soil, clay minerals or organic matter is basically centimole of charge per kg of soil. Now, you have understood why we are using this term, centimole of charge per kg of soil. Earlier, it was milli equivalent per 100 grams of soil. Now, it is centimole of charge per kg of soil. Again, this molar charge concept is, it is basically charge of 1 mole of substance. So, in case of 1 mole of calcium ions, the molar charge will be 2 because this is valency of 2. Similarly, for trivalent ion, the molar charge will be plus 3. Remember, 1 molar charge of any ion will be equivalent to 1 mole charge of any other ion, and that is why it produces a common baseline for calculation of CEC in soils. And since this mole is a bigger concept for easy, and it is difficult to manipulate this bigger unit while calculating the catenation capacity in the soil. That is why the most common unit is the centimole charge, which is 1/100th of mole charge. Okay. So, let us see one example. So, here first question is, what is the mass of 1 mole, 1 centimole and 1 millimole of the following cations and anions, that is H plus, Ca2 plus, Na plus, K plus, sulphate, nitrate and bicarbonate. So, 1 mole is the atomic mass or molecular weight per liter for each cation or anion, we know that. So, from the periodic table we can easily see what is the weight or mass in gram of 1 mole of these different ions. For example, in case of H plus we know it is 1 gram, in case of calcium it is 40, sodium 23, potassium 39, sulphate 96, nitrate 62, bicarbonate 61. So, obviously, mass of 1 centimole will be 100 of this molar weight. So, basically we are getting 0.01 gram, 0.4, 0.23, 0.39, 0.96, 0.62, 0.61, and mass of 1 millimole will be, when we are converting now it is to millimole, obviously we are getting 1 mg, 40 mg, 23, 39, 96, 62, 61. So, basically we are converting gram to milligram, and then that is basically mass of 1 millimole. So, this answer is pretty much simple. We just have to see the mass of 1 mole of these ions, and from there we have to calculate the mass of 1 centimole and mass of 1 millimole. Now, the second question is, what is the weight of 1 mole of charge? Now, we are converting into, now we are going into the molar charge. So, what is the weight of 1 mole of charge and 1 centimole of charge of the same cations and anions? Now, it is the atomic mass or molecular weight divided by the charge, we know that. So, here for example, 1 mole of calcium atoms basically gives 2 moles of charge. So, to calculate it, we have to divide the mass of molecular weight by the charge or the valency to get the 1 mole of charge. So, for example, the mass of 1 mole of calcium ion. So, for example, here we can see the mass of 1 mole of calcium is 40 grams, for example. Okay. So, the mass of calcium ions required to supply 1 mole of charge of calcium ion. So, mass of molar charge will be 40 divided by valency or charge, that is 40 divided by 2, that is 20. So, when we calculate the mass of molar charge, obviously mass of centimolar charge will be 100th of it. So, similarly for each and every one, so in case of H, obviously since the valence is 1, we are having the similar molar charge, mass of centimole charge is 0.01. In case of sodium, we are getting the same value in case of mass of molar charge and mass of centimole charge. K plus also same. In case of sulphate, it is 96 by 2, that is 48. In case of nitrate, that is 62, 62 same. In case of bicarbonate, it is 61, 61 cents. However, when we are converting into the centimolar charge, we are basically taking the 100th of mass of molecular charge. So, this is also very simple solution. Now, the third question is, what weight of calcium chloride would you need to replace 4 mole charge of potassium in a soil? So, you have a soil with, and you want to replace 4 molar charge of potassium in a soil using the calcium chloride. So, what weight you need? Now, we need to replace the potassium which is positively charged with positively charged calcium ions. Now, remember that each mole of calcium chloride has 2 molar charge supplied by the calcium 2 plus. We know that 1 mole of calcium chloride will supply 2 molar charge of calcium. Now, we need to replace 4 molar charge of potassium, and we know that 1 molar charge of any ion is equivalent to 1 molar charge of another ion irrespective of their valency. So, obviously, to replace 4 molar charge of potassium ion, we need 4 molar charge of calcium. So, to supply 4 molar charge of calcium, we need 2 molecules of calcium chloride, because 1 molecule of calcium chloride gives you 2 molecular charge of calcium. So, to get 4 molecular charge of calcium, you need 2 molecules of 2 moles of calcium chloride. So, 1 mole of calcium chloride weighs 111 gram. So, 2 into, that is 222 grams of calcium chloride will be needed to supply 4 moles charge to replace the potassium. It is very simple. So, we are starting, the basic concept is to replace 4 mole charge of potassium, you need 4 molar charge of calcium. To supply this 4 molar charge of calcium, you need 2 moles of calcium chloride, and just you have to multiply the molecular weight using 2. Now, the fourth query is how many mole of potassium does it take to replace 12 mole of calcium? It is also simple. Now, so we need to replace 12 molecular charge of calcium. So, obviously, we need 12 molecular charge of potassium. So, because it always takes 1 molecular charge to replace 1 molecular charge regardless of ion carrying the charge. Now, the fifth question is what weight of potassium is required to replace 2 molar charge of calcium. So, what weight of potassium is required to replace 2 molar charge of calcium. So, in the problem 4, that is in the previous problem, it was determined that 12 molecular molecular potassium are required to replace this 12 molecular calcium. Now, from the answer in the problem 2, that means that table where we calculated the mass of molar charge, we know that 1 molecular charge of potassium has a mass of 39 gram. So, we need 12 multiplied by 39, that is 468 grams of potassium ions to replace 12 mole of calcium ions. So, this is again simple. Again we need to have 12 molecular charge of potassium to replace 12 molecular charge of calcium. Now, from the calculated value of mass of molecular charge of potassium, we just have to multiply it. So, 12 multiplied by 39, that is 468 grams of potassium. Now, the sixth question is what weight of calcium ion is required to replace 12 mole of potassium. Now, we know that to replace 12 mole of potassium, we require 12 mole charge, 12 mole charge of potassium, we require 12 mole charge of calcium. But to supply the 12 mole charge of calcium, we need only 6 moles of calcium, because 1 mole of calcium can supply 2 molar charge of calcium. So, from the answer of problem 2, we have already calculated these molar charge. You know that a mole of calcium is basically 40 grams and that a 1 molecular charge has a mass of 20 grams. So, we can either solve it by multiplying these 40 into 6 or 20 into 12. So, ultimately the answer is 240 grams. Okay. So, we know that a mole of calcium is 40 gram. So, obviously, for 6 moles it will be around 240 grams. Okay. So, this is how we can calculate or solve this problem. Okay. So, guys, I hope that you have learned something new in this lecture, and in the next lecture, the last lecture of week 5, we will be talking about some more numerical problems related to CEC, and then we will be talking about thermodynamics principles as well as different equations to calculate the selectivity coefficients for exchange reaction. Thank you very much.